Hello, welcome to this video on the mean value theorem. We first start with a preliminary result. My name is Nakia. Thank you for watching. Hope you enjoy it. The preliminary result is called Rolle's theorem. It says the following. If you have a function f who is continuous on a closed interval a, b, and differentiable on an open interval a, b, one more thing, the f of a equals the f of b, the y values are the same at the endpoints, then you can conclude that you'll have a zero derivative someplace inside that interval. There exists some c value, maybe more than one, at least one for sure, where your derivative will be equal to zero. Now, we're not going to prove it here, but it's going to be something that you could prove, and I'll maybe put a link in the description for the actual proof of it. But here we go. Here's some examples where if your function is constant, it has a zero derivative everywhere in the interval. If your function is concave down, then you'll have a zero derivative inside the interval. Maybe you'll have more than one. Maybe you'll have a concave up function or have a zero derivative in the interval. These are all possibilities. It doesn't tell you where to find it, though. That's the only issue. It just says that you'll be guaranteed that it exists. Let's get an example. Cubic function, interval is from 0 to 3, and we want to find all the numbers that satisfy this. Okay. Polynomials are continuous everywhere, especially on the interval from 0 to 3. And they're differentiable everywhere, especially on the interval from 0 to 3, and not including them. Now, when you plug a 0 into this function, for sure you get a 2. When you plug a 3 in, it works out that you also get a 2. So we have all three conditions to Rolle's theorem satisfied. So we're guaranteed there's some place, this is the actual graph of the function here, we're guaranteed that there's some place where the derivative has the derivative is equal to 0. And that's it. So what are we going to do? We're going to take the derivative, end up with a quadratic. Not a factorable quadratic, unfortunately. But that's okay. We can deal with the quadratic formula. We can have a be equal to 3 and b be equal to -2 and c be equal to -6 and just plug it in. The c value that we're looking for is -b plus or minus the square root of b squared minus 4ac, all divided by 2a. Okay, not that bad. So when you plug it in, you'll get 76 underneath the rat. That actually has a perfect square that goes into it. 4 does. 19 times. We can pull a 2 out. And then what we can do is divide the 2 by the 6 and the 2 rad 19 by the 6. Break that up. And here are there's two values. One in which we going to have inside our interval, and one happens to be outside of our interval. How will we know without a calculator? Well, if you're already at a third and you take away root 19 over 3, since root 19 is bigger than 1, then when you take away that, it's going to be less than 0 for sure. Not in our interval. That's not the one we're concerned with. It's the other one. When you add root 19 over 3, how do we know that's not bigger than 3? Well, if you're at 1/3 and you want to add something to it and all of a sudden be bigger than 3, then the something that you add needs to be bigger than 8, and this guy is not for sure. All right, so it turns out that 1.79 is about the evaluation of that c value. So we did it. All right, Rolle's theorem. The condition, that third condition, is too much, so we're going to relax that. And that will give us mean value theorem. Let's save that for the next video. Thanks for watching. My name is Nakia. Please like and subscribe. Comment down below. I'll see you in the next video where we actually state mean value theorem and we'll actually prove mean value theorem using Rolle's theorem, of course. Take care. Bye-bye.